Alright, time again for another DraftPhysics.com video presentation. The second in a series of videos responding to, well, this guy, Jason, I believe. And again, on the subject of gravity, and, it's really elemental in physics. I could almost argue that the physics, the mechanical idea of what happens when energy goes into something and energy comes out, really elemental to physics, and of course they have it all wrong. Not even close to the truth. So that's what we will go over, and such, and so forth and whatnot. So, we're 10 minutes in, and we got a long way to go, and we'll see how much of it we'll go through, but whatever. It's all fodder for a conversation about just these simple elemental functions, and as I've argued, gravity is really just, an inverse square law. That's all it really is, and the inverse square law is associated with radiation from, say, an explosion. The little pieces will fly off at the inverse square law, in the sense that they'll separate from each other as they go through space. They'll be getting further apart in 2 dimensions, and that makes the square. So there's 4 times the area in twice the size. So you make it twice as big, now there's 4 times the area that you're spreading something over, so it gets 4 times weaker. And if it's the inverse, that is, the energy is coming into you from the universe, let's say, in all directions and in all ways, you're just basically doing the same thing. You're taking stuff that was spread out and it's coming into you and converging, and it's doing it by the same inverse square law, in the sense that it's moving this way, okay, and it's getting closer and further from each other, you could argue, in these dimensions. So this motion you can't mess with, but these dimensions, you can see when it's converging that these dimensions are contracting. So the distance in the space between particles of stuff that are going to hit you is reducing at the inverse square law. That's gravity in the sense of how it gets to you. And the simple argument is it's energy in, energy out. And so you're stuck in that differential. The energy going in hits you first. The energy that will eventually come out has to go through the dense matter. It's slowed down a little bit, so it doesn't get to you at the same time the energy from the universe is hitting you. And therefore, you're falling, you're being pushed in that differential. So that's the simple argument. It's really, really simple. And the Earth is proving the point, because what happens, that slowing down has a consequence. It's friction, essentially. And the Earth is all molten and melted because of that function, because it is interacting with a bunch of force constantly coming in from all directions, and it's trapping some of that motion for a moment of time until it has time to dissipate out again. And so you can see the heat differential is kind of obvious in the fact that the Earth is melted. Alright, so with that preface, leave us play the video.
Theory of gravity. But if someone makes a model of a quantum theory of gravity that predicts things better, then we will think that that is one more step closer to truth.
So again, this quantum theory of gravity, just again, their idea of quantum is wooey, superposition, entanglement, mush, when quantum really means discrete small bit. Okay, so when Einstein talked about light quanta, he was talking about clumps, and it's that simple, that the force comes in clumps. And so, as what I've just described to you is the opposite of an explosion. You can see they're clumps of stuff, and that's exactly what light is, and that's what all energy is it's always in a clump form. It's either in the form of stuff moving the speed of light, being very tiny, or it's in the form of electrons and protons being pushed by the force.
So, knowing that Newton's law of gravity is not as good as these other theories of gravity is...
So this is just nonsense. So there's no real evidence that it's not as good in any other place in the universe except the precession of Mercury. And again, that has more to do with the fact that you're just jiggling the sun. So Einstein's complex equation is really just taking some notion of the speed of light and contracting size and warping space and using that to essentially jiggle the sun.
Is it worth studying? Answer is yes. It is absolutely worth studying for a couple of reasons. The reason we study Newton's law of gravity is because it allows us to solve problems that are not so difficult and you can learn a lot from them.
Okay, the point is that Newton's theory of gravity was essentially, I don't have an explanation for the cause. But again, he articulately and accurately described the effect. And so, there's all kinds of nothing wrong with the idea that it's applying a pressure or a force. He accurately defined the way you can calculate that. The gravitational constant is not inaccurate. So again, it's just sort of bullshit to argue that there's something mechanically wrong with the mechanism Newton provided. Now, obviously, what Newton didn't do was say, well, the ground is, the earth is molten, and you have to account for all that energy. Where did it come from? Well, it obviously comes from this process of gravity. That's the deficit we're falling into. There's a whole bunch of heat in the earth, therefore, where did it come from? What came from? That's why we're missing some pressure pushing us against the gravity. Duh.
Number two, even though it's not as accurate as Einstein's theory
he said it again. Oh, poop.
of gravity or other theories of gravity, it is perfectly fine.
Well, whatever this other theory is, I don't know. What other theory of gravity that's more accurate than Newton? I don't think so. It's just ridiculous. Look, the problem is Newton didn't have a cause, okay? He thought about different particle theories. He thought about different kind of ether theories. He thought about them, and he couldn't make any of them work. And that's partially, in my opinion, is just because he didn't know there were electrons and protons. And he didn't clearly, when he was first thinking about this stuff, he didn't know there was this speed limit, this idea of, light moving a constant speed.
To make calculations with Newton's theory of gravity that are accurate enough to send a spacecraft through the solar system, for instance.
No, yeah, it's accurate enough to land one on the moon. So why don't you just tell the truth, that they didn't use Einstein to land on the moon, they used Newton. And they didn't use 1/2 mv squared, they used mv, they used quantity of motion. So, they can't tell the truth. So, this is, it's a futile argument if lies are okay in this court. And it's just a lie to imply that this other physics does a better job, because what's better proof of the good job it did than we landed on the moon multiple times successfully?
So even though it's not as good, it is good enough.
He said it again. Jesus Christ. So it's not as good, but it's what we used when people's lives were at stake and billions of dollars were at stake. This is what we used, but it's not as good. Oh, fuck.
To send space probes to other planets is very, very useful, much, much easier to calculate. It took Einstein 10 years to develop his theory of gravity.
All right, so let's just understand it. He certainly proposed something, and then he had to defend something. So let's just understand it took him 10 years to try to contrive a defense of it. So that's sort of a bullshit description of the reality also. I'd be back. I should be back.
So if it took Einstein 10 years, then the mathematics is difficult enough that it is very, very difficult to do simple calculations with. So we always start our journey in physics learning about Newton's theory of gravity. We use it, but then as you continue your studies, you'll learn about other theories of gravity, which are a touch more accurate, but also...
Okay, so again, the accuracy is something I've never seen proven. All right, but we are supposed to believe it's somehow better, that it does other planets better, or does something, asteroids better, or does anything better. And I haven't seen any evidence of that. And all I've seen is that, again, if there is some, you know, inconsistency in the density of the sun, which is perfectly plausible, just as there's inconsistencies in the density of the earth, that could be the explanation for the precession of Mercury. And you can create almost, there's a million different ways you could mimic the exact same behavior with any configuration of unevenness in the sun. So it's just kind of bullshit.
So much, much, much harder to apply. The mathematics is much, much harder. All right, so that's a ton of talking.
I could give you the financial mathematics of doing the Eddington experiment from space. And the financial mathematics are that it costs 1 million times less, okay, than gravitational waves and neutrino detectors and all the other crap that physics wastes all this money on. So you can do this experiment where you can make it actually visibly possible to see light bent twice as much by gravity. So the fastest, lightest thing in the universe we are supposed to believe, because they say so, not because they show you so, because they say so, is twice as bent as any other material object in the universe. And the very fact that it's bent at all should be reasonably suspect, because you can't bend forces with forces. You can't bang photons into photons and bend them or deflect them. You can't deflect photons with magnetic fields. You can't deflect photons with electricity. You can't deflect photons. You have to use particles to deflect them. You can't deflect them with a force itself.
Okay, I just wanted to give you the big picture before we get into it.
Yeah, the big picture. Yeah, sure. Oh, we are back.
Now, one thing I'm going to say before I write the equation on the board. Gravity is the weakest of the four fundamental forces of nature. Let me give you an example of how...
So why would you go over this and over this and over this? It's just a silly argument. It's being created by a unique circumstance of it being a transmission problem. You're transmitting energy through material objects, and that's obviously different than just sending it across the atmosphere or something.
It's so weak, all right? This body of mine is attracted to the ground with a gravitational force. I'm being pulled into the ground. Now, the Earth is really, really big. The Earth is huge, and I'm just a tiny little speck standing on the top of it. And every particle of matter in the Earth is attracting my body down.
So that's not exactly the way of explaining it, right? So it's not attracting, and every little particle of the Earth is actually absorbing a tiny bit of the energy that's going through it by moving, and it takes time to move electrons and protons. They don't move as fast as the force. So you can understand this force doesn't get where it would have been if it wasn't pushing electrons and protons. It would have been further. And that's the simple explanation. But yes, they are saying it's some sort of pulling, magical pull thing. And yes, we're gigantic by comparison to the size of an electron. So obviously there's a pretty silly comparison to make, to talk about how one electron is supposed to gravitationally pull us into it. Of course, that's not going to happen.
The entire Earth, through the gravitational attraction of every atom in the Earth, is what is holding my body down with whatever I weigh, 160 pounds, 170 pounds, whatever it is, of force acting in the downward direction. But if I spring my legs up and down and just apply a force, I can break free of the theory of the force of gravity momentarily until it stops me and it pulls me down. So I can jump, right? So gravity we think of as very strong, but actually it's so weak that the entire planet pulling on my body can be overcome.
I just don't get this. I just don't get this comparison. It's apples and oranges. Again, it's like comparing somebody who's running carrying 15 watermelons, okay, and somebody who isn't. Why bother making the comparison? Say, oh, the guy carrying those watermelons is so much weaker. He's not weaker, he's in a completely different circumstance.
By my simple little legs. And my legs are powered by muscles, and my muscles are powered by chemical reactions.
And yes, and we could, if we thought about how many electrons you're moving, it's trillions of times more. So obviously we're using an insane, huge, gigantic amount of energy. So there's no point in comparing it to the relationship between an electron and the field energy that it's using to reflect against, repel against another electron, when, it's a tiny amount of force compared to how much force it takes us just to blink our eyes.
Reactions, which is all governed by electric forces, because any chemical reaction is electrons moving around in substances. So when you think about it, this electric force is so much stronger than gravity because the tiny amount of mass in my legs can overcome the force that the entire planet is exerting due to gravity.
So we know it's not the entire planet exerting, it's the entire planet consuming. And if you actually look at how much energy it's consumed, it's melted an insane amount of matter. So yeah, it's one hell of a furnace. If you had to actually go buy the coal to melt the earth, you'd have a pretty expensive bill.
Now, the upshot with gravity is that it applies over vast distance scales. So we can have enormous collections of mass in galaxies and solar systems and nebula. And so when you add up all the gravity, it can get quite strong over far distances. But over smallish distances, it can be demonstrated how weak it is by simply jumping off the ground. I can overcome that force there. All right,
so again, I just don't get it. I can't even understand why you would think it's the same mechanism. It's not the same mechanism. The Earth isn't a charge. It isn't an electron. It isn't a proton. It's not doing the same thing an electron is doing or a proton is doing. So why bother with the silly comparison?
Now it's time to talk about Sir Isaac Newton. Certainly one of the most intelligent, brightest, gifted people to ever have lived. If you ever read about his life, it's amazing reading about his accomplishments at such a...
Well, again, let's see, the gift was that he had an insane work ethic and spent all of his time doing one thing, trying to pursue these answers, and that's it. He didn't do anything else but that.
Young age, okay? So the story goes that he was sitting under an apple tree and watching an apple fall and hitting the ground, and also looking at the moon in the sky, and wondered, could the same force that pulls the apple down to the ground, could that same force extend all the way up into space and be applying that force onto the moon? And if that's the case, could that be an interaction between the Earth and the moon that allows it to go and orbit the sun, or orbit the moon to orbit the Earth? Could that same force that governs apples close to the ground...
Right, so he was thinking about moving the apple. So he didn't just stop with, what is it, the same force? He had to figure out the orbiting part and say, well, what would happen if I push the apple? And what if I push it faster, and I push it faster, and I push it faster? Then it's going to do the same thing the moon is doing, essentially, which is it's going to keep missing the Earth. The Earth is curved, and it's going to keep missing it.
Stretch out into space and govern the motion of the planets? That's the question. So there were a lot of people back in that time, about 300 years ago, plotting the positions of the planets and monitoring them. And they figured out that all planets are actually in elliptical orbits about the sun. Elliptical orbits. Most people think orbits are a circle, but actually...
This is another small point, so I don't know why they're really obsessed about this, because this just has to do with the formation, how you get into an orbit. And so it's essentially this highly improbable thing that you could ever possibly move a velocity and get into a perfect orbit, because your speed is wrong. So as you're going into the gravity, there's no position you can have a velocity that you can get into a position where you'll be the right speed for the orbit. So the only way you can get into the orbit is something has to happen to change your velocity. And so that's why the orbits are always eccentric, is because there's no way to get into a perfect one unless you engineer it. Like, we can go up into orbit and we can engineer the orbit and make it perfect. Or we can make it as imperfect as we want to. So lots of times when they're doing these satellite missions and they want to keep the satellite in the system, the Jupiter system, for example, they're going to jump from the moons of Jupiter and do some photographing, and the thing will spend 5 years just bouncing around inside the solar system of Jupiter. Just because of the eccentric orbits you can create.
The planets orbit in an ellipse, with the sun at one focus of the ellipse. And you learn about ellipses in math class, in algebra class. But an ellipse is basically an egg-shaped orbit, and the sun is at one of the foci of the ellipse. So Newton asked himself, if the force that's pulling on the apple is the same exact force that's pulling on the moon, and if we know the shape of the lunar orbit is elliptical around the Earth, and we know that the Earth...
So we know the ellipse is tiny. It's not a very big or eccentric ellipse. It's a very small, it's just a little bit off a perfect circle. And the Earth's orbit's only a little, a couple of degrees. They're very, it's not a huge ellipse. It's very close to a circle ellipse.
This elliptical orbit around the sun, which is very controversial, but if you take that to be true, what must the force equation look like to produce an elliptical orbit? That's what he worked on. Right? He said, what must the mathematical form of the gravitational force be in order to produce a motion around the body that's orbiting as an ellipse? Not some circular or some other, because there's many mathematical shapes. There's parabolas and hyperbolas, and there's...
So I don't think this is true. I don't think this ellipse issue was anything more than Newton accepting what had already been discovered. And I really don't think it went any further than that he thought the ellipse was essential to understanding how strong the force of gravity is, because I think he already knew that all you need is the force. And you can make it round, you can make a perfect orbit, or you can make an imperfect one, and it doesn't matter. So I don't think that was a challenge to him at all.
Circles and lines and all kinds of things, but we're saying it forms an ellipse. So what must the form of the equation of gravity be in order to produce an elliptical orbit? And he crunched through it and figured out this is what it must look like. And so we'll just reveal the punchline. If...
So again, the inverse square law solves the problem, and then you're just figuring out what you need. You need some sample of some object with a density to figure it out. And so what he used was essentially the moon. And so he used the moon to essentially give him some idea of a potential size of an object. And so he did a rough estimate of the 1/6, the size and the mass, and then he did what the figuring would be, and that's basically how he got his rough sketch.
You have a planet over here, or some body, anybody, could be anything, and another body over here. And this body has some mass, we call it M2, could be the Earth, let's say. And this mass has a mass, or a body has a mass M1.
So this is the just waste of time, where you don't need to have both objects in the equation to calculate the gravity of each independent object. So it's just a waste to imply that you need both objects to calculate something's gravitational force, because it has it regardless of anything being in the field. The Earth doesn't need the moon to have 9.8 meters per second of surface gravity. It's just irrelevant. The moon doesn't play any part in the Earth's gravitational field.
And we're drawing circles here, but these bodies could be any shape, right? Then
no, they really do have to be spherical. So again, they can't be any shape. So that we've already discovered too, because they found that these asteroids that they put the satellites up near, that their gravitational field changes. So it does depend on the shape of the object. So misshapen objects will have uneven gravities, because gravity really isn't being, the gravity is explicitly being caused by the mass, and its location is critical. So if you want to have even gravity, you have to have a sphere.
And if these bodies are separated by some distance r, you could call it distance d if you want, whatever, call it whatever variable you want, then there is some gravitational force that exists between them, right? We know that this body is attracted to this one, and so we draw a vector.
So, okay, attracted is always the wrong word, so yes, they're both pushed into each other. That's the fact of it. They both shadow each other, in a sense, from the field energy, and they move into the shadow.
Vector pointed this way, and we call that a force of gravity F sub g, and we put a vector bar on top of it. And then we know also that this one is pulling on this one, so there's a force that way, but this body is also pulling this way.
And so it's just wrong. I mean, I don't want to, I can harp on it, but I mean, it's wrong. There's no pull in the universe. The universe is made out of pushes. So what there is an absence of push between them. And so that absence of push means that the push on the outside is going to win. And it does.
Like this. And that's also called F sub g. Now, I've tried to draw the lengths of these arrows the same. I may have not succeeded.
Yeah, well, but just put them on the other side, and obviously they're not going to be the same. They're two different sized objects. Shit. So why are you trying to make them the same when you draw the objects as being, one is at least 3 times bigger than the other one? 2 times.
But they're attempting to be the same exact length. Because it turns out that the force that's exerted on this planet pulled that way is exactly the same as the force on this planet pulled that way. They're called F sub g, right?
Yeah, that's just nonsense. So the force being absorbed by the 2 objects is going to be quite different. So an elephant absorbs a hell of a lot more force falling in gravity than you would. And you can see it when it hits the ground. The elephant's going to disturb an awful lot of ground, and you'll disturb much less ground. So we know it's collecting a lot more force, so it's just silly to say it's the same force. It's not the same force. You need a lot of force to push an elephant. You need almost no force to push the feather.
Now, I'm going to talk a whole lot more about why those forces must be the same, but it comes down to, remember Newton's laws. For every action, there's an equal and opposite reaction.
Yeah, so more bullshit. Bullshit interpretation. Frankly. I mean, again, I could just give this simple argument. If I give away $10, there's no opposite action that takes the $5 from me. If I give away $5, I have $10. I don't get $5 poorer because some other action shows up and takes my money. No, I already gave it away. I already lost it. I don't need a second action to change anything.
So if you pull one direction, if they're interacting
if
through...
If you give away going this way, like a rocket engine, I give away a whole bunch of stuff going this way. I still have inside of me a whole bunch of stuff going that way, and now they're not even. So now I'm going to go that way because I gave away the stuff keeping me here, which was the stuff going this way. You have a tank and it's full of stuff, and some of the stuff's going this way hitting that wall, some of the stuff's hitting this wall, and it's equal. Well, if I give away all the stuff that's going this way, that is, I don't let it hit the wall, I just shoot it out the exhaust, well, obviously now I don't have the same amount of stuff going this way as I have that way.
A force, then the forces have to be equal, and they have to be acting on the opposite body, basically. We'll talk more about that in just a second. But
so it's all wrong. It's, again, they call friction a force. Friction isn't a force. Friction is just you hitting things and giving them your energy, period. End of that story. You're just transferring your momentum from you to them, to it, to the surface.
There's a mutual attraction between these two. And if you were to let them go, then they would drift towards each other until they finally collided, right? And Newton figured out that this equation that governs this force must...
So the force is not going to be the same, but the velocity will be. Blah, 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 blah. But it won't be, because this one's in a much weaker gravity than this one is. This object's going to be in a much stronger gravity. It's going to move much faster. This one's in a much weaker gravity, a little tiny gravity made by this, and it's going to move a lot slower. So he didn't do this very well.
Look like this. It must be the following. F sub g must be some gravitational constant, capital G. This is different than lowercase g that we've been using. 9.8 meters per second squared, that's a different number than this. This is capital G.
Right, and so this is the constant that creates that number based on the mass and your distance from it. So it gets you the 9.8. And it's why there was a 9.8. This can be deduced if you know what the mass is. So obviously at the time Newton didn't know what the mass was. And so Cavendish essentially measured the mass of the sun, and by measuring the mass of the sun, measured the mass of the earth and everything else. But anyway, So what he's going to do here is make this fraction more complicated than it has to be. So the g is sitting here. Now he's going to put m1 times m2 when he could do m1 times g and then m2 times g. And you'd see that it's just a plus then. Then you'd just be adding the two fractions, and obviously you could just say, well, what's the force of the Earth? Well, I'll just do the force of the Earth is just going to be the mass times the constant divided by r squared. There, done. So this equation looks like you need to have both bodies, and no you don't.
Multiplied by the mass of body 1, then also multiplied by the mass of body 2, but then divided by the distance between them, but not just the distance between them squared. This is...
So, again, the inverse square law just has to do with spherical symmetry, so that can be understood, and so it's just telling you twice the distance, 4 times the change in the intensity of the force, whether you're going in or you're going out. So again, you could just change the equation to g times m1 over r, and now you know the force created by mass 1. And if you want to know the force created by mass 2, then you just do g times mass 2 over r squared, and you have the force created by the smaller object, and then you're done. Well, in this case, bigger. m2 is bigger than m1. So you're just adding two forces. There's nothing, you don't need them to both exist. So this idea of multiplying the masses gives you this impression that somehow both masses have to be in the equation, and they don't.
The famous Newton's law of gravitation.
It really is silly to make the law of gravitation and put another object in, because it's completely superfluous. The law of gravitation is simply F equals g times the mass divided by r squared. That's really all there is.
Through experiment, which we're going to talk about in just a second, determined experimentally we can calculate the value of g. And so we know what this universal constant is. It's 6.674 times 10 to the negative 11, and it has some crazy looking units. It's Newton multiplied by meters squared divided by kilograms squared. All right, what does this mean? First of all,
so the units, I think, are just garbage, frankly. Completely superfluous and unnecessary.
He calculated that the force of gravitational attraction between two objects is the product of their masses, but then divided by or inversely related to the square of their distances. So, and this whole fraction here is just multiplied by g, but g is just a number. Don't get so freaked out like by the units. It's got some units, okay, but it's just a tiny number, right? It's a small number, 10 to the minus 11. It's just some number. It's a constant of proportionality. In other words, he figured out the...
It's just a number to establish, because we created units of meters and seconds that are not the units that would make that constant 0. So if we just change the meter to a different size, we can make that constant go to 1. Or we change it a second to a different amount of time, we can make that constant go to 1. So we can get rid of the constant if we just change what units we're calculating in.
Form of the equation by saying, okay, we know the planets go around the sun or around the earth in this shape, this elliptical shape. We know the mathematical shape of an ellipse. Let's say that that shape is governed because of some force of attraction to the planet that's involved. What does that force of attraction need to look like mathematically to trace out that elliptical shape? And when you work through that mathematics, the equation that works is an inverse square law, is what it's called, where it's proportional to the two masses multiplied together but then divided by the distance. What this means is, if I increase the mass of this planet, then the force of gravitational attraction goes up. That makes sense if there's more mass, right? If I make this bigger, then I'm multiplying, I get a bigger number on top. And
I mean, again, and so you don't really need the number, because all masses will orbit exactly the same and in exactly the same position. So I put an atom next to the moon, it'll do exactly what the moon does. So the force is going to affect them proportional to their mass. So it makes no difference. The light thing will get little force affecting it. The heavy thing will get a lot of force affecting it, so they will move exactly the same. So I don't ever need to use this combined formula. This combined formula doesn't mean anything. It's of no use. It's always just better to understand that each object is creating a gravitational differential. And I just add the gravitational differential. So if I want to know anything in space, I just figure out, well, what's the gravity of this object, what's the gravity of that object, and I just add that together.
I get a bigger force if you hold everything constant. If I increase the mass of the other object, then same thing happens. I make this bigger, and then the force of gravity is bigger. But if I make them farther apart, then the denominator gets bigger, but not just bigger, it gets bigger squared. So if I make the distance twice as far apart, then basically down here.
So this is just the same exact thing as the sun. So the inverse, the sun, the radiation coming off the sun is duplicating the inverse square law. It's exactly the same thing. So you can perfectly understand that, yes, you're spreading the force over a squared area. And the squared area means that, twice the diameter, 4 times the area.
Here it'll be 2 times the original distance, and when you square it, 2 squared is 4, and so if I double the distance, I'm going to be dividing by 4 on the force. So if I double the distance, my gravitational force is 4 times weaker. 4 times weaker because if I put a 2 down...
See, they could have used d squared, okay, and then they'd have to change the gravitational constant. Doesn't really matter what length unit you square, but obviously when you do that, you'll have to change the other unit to fit. So the gravitational constant would be 1/2 of what it is if you changed the r into a d.
Here, like double the distance, 2r, 2 squared is 4, right? So if I double the distance, I cut the gravitational force down by 4 times.
So, I mean, you can argue that it's the diameter of the Earth that's really absorbing the energy. It's the full diameter underneath me that is delaying the energy to get to me. Okay, it's not just going to the center, but that's how it looks from our perspective because there's stuff pushing from both sides. So that's the collision point, is in the center, but there's no real collision.
So you can see that the stars that are very, very far away, they are attractive, but they're so far away that those gravitational influences are so tiny on us, we don't feel them. Now,
so we don't feel any gravitational influence. So you'll never feel gravity because it moves all of your bits exactly the same speed. Just like the feather falling the same speed as the lead ball. The same thing's happening inside of you. All your pieces are falling the same speed. They're all moving the same speed, so you can't feel any differential.
a couple additional things I want to say qualitative.
You can only feel something because one part's moving differently than another part. If they're all moving the same, you can't feel anything. Feelings about a difference. When there's no difference, there's nothing to feel. Fact.
Qualitatively, before we jump into solving a problem, I want to talk a little bit more about this because we really have to, I want you to get very comfortable with this, right? So we said if we increase the masses of the bodies, gravity go up. We said if we increase the distance between the bodies, gravity goes down, but it goes down by the square of the distance. We have this constant of proportionality out here called the gravitational constant. Notice the weird units here. If you put these units here, okay, let me ask you, what are the units of mass? It's kilograms, right? And the unit of mass here is kilograms, right? And the unit of a distance is meters. So this is meters.
Yeah, so what? Kilogram times a kilogram, is that a kilogram squared? I mean, a meter times a meter is a meter squared. So why isn't a kilogram times a kilogram squared? I mean, it's too ridiculous.
Squared. So on the top here, with forgetting about the G, it's going to be kilograms times kilograms is kilograms squared. And then it's
too ridiculous, right? It's just ridiculous.
Going to be meters squared right here. So you have kilograms squared on the top and you have meters squared on the bottom. We want the unit over here to be newtons, right? Because it's a force that you're calculating. So the units of this G have...
It all ends up being pressure or weight, and that's all there is. It's just momentum. So it's all mv in the end. So all of these nonsense units as just that. You're just calculating a momentum, which is a weight.
To be like this. They have to be meters on the top to cancel with the meters on the bottom. Meters squared on the top to cancel with the meter squared on the bottom. And it has to be kilograms squared on the bottom here in the unit to be canceling with the kilogram squared on the top here. So
right, so just a pile of nonsense. And if you didn't have the constant, that is, if I used some other version of a second or a meter or a kilogram, if I used some other weight or some other, like if a kilogram was some other amount of weight other than a kilogram, then I can change the constant, and I could get the constant to be a 1, and then you would have no constant to multiply by, and therefore you'd have no units to multiply by, and you'd have no way to fix your silly equation. Okay.
The only unit left when you do the multiplication is going to be newtons. So that's why we say the units of this G is so weird looking. It's because the units have to cancel to give you newtons at the end.
Yeah, so it just shows they just contrived the mass. There was never any kilogram squared. Okay, it's just silly, right? There's two objects, it's their mass, there's no squared kilograms. So that was a silly thing to have happen. You're basically just multiplying the two entities and that's it. You're not squaring that answer. There would be no reason to square that answer.
All it is. So don't get so worried about things like this. Right now, one misconception that a lot of people have, even me when I first learned this, is that, when you have like a planet and you have like an astronaut, the planet has like a really, really big mass, and the astronaut has like a really, really small mass. And so you think that the gravitational force on the astronaut from the planet is going to be like big, and you think that the astronaut pulling on the planet is going to be really, really small. But
yeah, exactly. So I don't know how he's going to undo that as being the truth. That's exactly the amount of force the astronaut is applying in the universe in terms of gravity is so minute that it wouldn't be able to move much at all. It can't even move a piece of styrofoam. It's so minuscule.
Actually, according to this diagram here, you see you have the same amount of force pulling on this tiny little mass as you do pulling on the other mass.
No, you don't. So it says it's just ridiculous. That's just not true. So that's just ridiculous. I don't know why he thinks that's possible or has something to do with reality. Tiny things create tiny amounts of force. Big things create gigantic amounts of force differential. And you're just saying, how much did it consume? How much heat did it consume? Big things consume lots of heat. Little things consume almost none. It's just, it's just ridiculous, frankly. I don't know how you could get that wrong. And it's just frightening, frankly. I mean, like I said, he worked for NASA, so come on. Did he do nothing? What did he do there?
Because this gravitational force, it's not telling you like a one-sided force, one thing pulling on another thing. It's predicting the mutual forces acting on two different bodies. Let me say that again. The gravitational force equation from Newton's law of gravity, it's not predicting one force or another force, it's predicting a pair of forces. So what it's saying is the mutual force, Fg, that exists between two different bodies is proportional to all this stuff when you multiply and divide and multiply.
Yeah, so you don't need any of that stuff. It's just the G times the M r squared, G times the M2 r squared. Those are the real forces, and they're going to be gigantically different. The big object's going to have a big gravitational force. It's going to be applying a huge differential in the field, and the small object's creating a tiny differential in the field. All right, so geez, that was disappointing.
You get a final number. But Fg that you calculate, it's not like a one-sided thing. It exists as acting on both bodies. And you might say, well, that doesn't make sense. The Earth is very, very large. It should pull harder. And the astronaut's very, very small. It should pull smaller. But you have to think in terms of action-reaction pairs. Remember back to Newton's law of motion. Every action, equal and opposite reaction, but those forces always act on opposite objects. The action-reaction pair, they act on the opposite, basically they're due to two forces between two bodies, and they act on the different bodies. So if my hand pushes on the board, that's...
it's just wrong. But anyway, yes, you push on the board, and the board pushes back with the same force you applied. So it's just using the force you're pushing in with, and it's just throwing it back at you and using it to push you away. Because the electrons in the board are elastic. They actually are elastic. They can absorb a force and then give it back.
It's a force acting on the board. The reaction force is the board pushing on my hand with equal and opposite force, right?
And it's only equal and opposite because you increase the pressure inside the board. So just like us, we push into the earth, we increase the pressure in the earth, and so now the earth is going to push us back with that increase in pressure.
Notice that those two forces are acting on different objects. I have one force acting on the board, and the reaction force is the board.
So there's no reaction force. It's just wrong, but okay, whatever. There's no new force applied. There's only the one force. If the board moves, then clearly where's the equal and opposite reaction? There isn't one. Right? So if I hit, if I push on something, push on this air, it's not resisting, it's being pushed. Where's the equal and opposite reaction?
Acting on my hand. Those two forces act on different bodies.
I mean, then you have to start talking about my feet absorbing energy through the ground because it's stopping my body from going in the opposite direction. So now you're changing the whole thing. So in his example, he's saying there's an equal and opposite reaction here, and then there's also an equal and opposite reaction in his feet. So now he has too many actions and reactions.
But it's the same exact magnitude of the force acting on different bodies. Another example might be...
All right, so listen up.
So it was a terrible example just because gravity is... Big objects make big gravity, little objects make little gravity. It's not the same gravity. So it's just wrong. Commercials.
This is anchored to the ceiling, let's say, and it's rigid, and I'm going to pull down, right? I'm going to pull down. I have a force acting on the ceiling. Well, through this.
So you're pushing down. Actually, you're pushing on you're pushing on it. You're not pulling on it.
Rod. I'm pulling. It's a pulling force. I'm pulling down.
No, you're pushing down.
So that I have a force acting on the ceiling. The reaction force would be the ceiling pulling up on my hand. But those two forces are acting on different bodies. One of them is my hands pulling on the ceiling, and the other one is my ceiling pulling on my hand. They're acting on the opposite body.
So it's just wrong. I mean, like I said, there's an equal and opposite reaction, but it isn't created by anything other than the fact that everything's elastic, essentially. So it's the same force just being rejected, essentially.
So action-reaction pairs always act on the opposite body on a two-body interface or a two-body interaction. And it's exactly the same thing with planets. It's like there's an invisible string here, and they're although it's a little different because there's nothing there, and they're kind of attracted to each other like this. So the string would get like it would.
Whatever. So there's no string pulling. There's force pushing the two objects. One of them's being pushed by a ton of force, like an elephant, lots of force. If it hits you, it does lots of damage. The other thing, the feather, very little force, hits you, no damage.
Get loose, and it would just kind of like shrivel up and such. So it's not really the same thing. But to get the idea, since it's a mutual interaction between two bodies, you have one attraction acting on this body, and then the other attraction is acting on the other body, but the forces themselves are the same. It's very, very important for you to understand.
So it's just idiotic. There's no same force. It just doesn't make any sense. I don't know why you would say it. It's just crazy. Different force on the moon than there is on the Earth. Different force. It's completely different amount of force.
All right. Now, you might ask, well, if that's the case, why can I can feel the force of the Earth, but the Earth doesn't feel the force of me? Well, actually, let's talk about that a little bit more. Let's say that you have...
The Earth certainly doesn't feel the same force, but whatever.
A situation with Earth, and then over here you had some astronaut just in space, right? Obviously, the mass of the Earth is much bigger, that's what the double arrows mean, much bigger than the mass of me, the astronaut. I'll go ahead and put my little smiley face right there. Mass of the Earth is much, much bigger, but according to Newton's law of gravitation, the product of their masses, the product. In other words, Newton's law of gravitation doesn't just say, hey, look at the bigger mass and tell me the force. It doesn't say, look at the smaller mass and tell me the force.
But that's the truth of it, okay? So again, you just rewrite that formula as g times m1 over r squared and g times m2 over r squared, and you've solved your problem. They're two independent sources of force, and there's no reason to combine them, frankly, because one is very large and one is very small.
Because the product of the masses is what's important. The multiplication of the two masses. That means that both masses determine what the gravitational force will be, not one or the other, even if one's much bigger. It's the product of their masses that matters. So Earth is very, very large. I'm very, very small, but it's the product of their mass.
Right, and if you put something between these two objects, you'll see the huge, gigantic differential, because if you want to have an equal force between the two of them, you're going to have to put it right up next to your fat head, right there. I mean, you have to barely go a distance. Any distance from the surface of the person is going to already be less gravity than the Earth's creating. At almost, this distance would have to be astronomical for you to start being more gravitational than the Earth. It would have to be like you're out in Jupiter's orbit, feeling the Earth's gravitational pull before you'll be able to put the object maybe an inch from your body.
Masses and divide by their distance here, and so there is a gravitational force right here called Fg, and there's a gravitational force right here, same length of the vector arrow, called Fg.
I mean, it's just no point in doing that. It's just not right. I mean, the force neutral, the force equal, is not going to be in the center. It's not going to happen.
The forces are the same, but they're acting on different bodies and they're acting in opposite directions. All right? Obviously, if you let them go, they're going to come float together. Now, if I'm in orbit, I may try to orbit around. We're going to talk about orbits later. But if you're not in orbit and you just let go, then I'm going to slam into the Earth. Now, you might say,
yes, you're going to slam into the Earth. The Earth isn't going to slam into you. So that's going to be the absolute fact. The Earth is not going to come to you. You're going to go to it.
well, okay, but the astronaut is going to be the thing that moves. The Earth is not going to move. The Earth is not going to like float up to me, but actually, think about it. This is a force of gravity acting on the Earth. This is a force of gravity acting on the astronaut. But if you remember, right, from Newton's law, force is equal to mass times acceleration.
So again, that's not even right either.
And force is
not Newton's law. Newton was a momentumist.
Equal to mass times acceleration. What I'm saying is that this gravitational force would be acting on the Earth. So I can say Fg, right? And this gravitational force would be acting on the human, Fg, right? But the mass here is huge. And the mass here is tiny, 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 right?
I know. That doesn't change the fact that they're still not the same force, being the same force differential that the two objects are experiencing. You, in fact, are experiencing the huge differential. The Earth is experiencing an almost infinitesimally minor differential.
So if I have a very large force and I divide by something small, I can get a large acceleration. But if I have the exact same force acting on the Earth, the mass is so big, if I divide by m, like if I just say, well, what is the acceleration going to be? It's going to be the force of gravity divided by the mass.
So this is another way they're manipulating the math to tell the story all wrong. So yes, it's true that if you want to play this game and say it's the same force pushing smaller and bigger objects, but it's inverted to the cause. The cause is the fact that the Earth is gigantic, creating a huge force. You're small, so you can go into the force very easily. I mean, that's all there is here. You're easy to move.
The mass of the Earth is huge here, so the acceleration of the Earth is so tiny I can never ever see it. But over here, the acceleration of my body is the force of gravity divided by my mass, but my mass is very, very much smaller, and so my acceleration can...
So it's the force that was very, very much smaller. So again, there's just no, there's no real point. But obviously, It's a small, tiny differential the human creates. It's a huge, giant differential the Earth creates.
You can actually see it. So the bottom line is,
our surface gravity is, 0.000, probably 40 zeros before you get to a 1.
I stand here on the ground, right? The Earth is pulling down on me, and I am pulling up on the Earth, and we are pulling on each other with the same exact force.
But, all right, so it's just, I don't know. There's no point in me saying it over again, but that's just completely wrong. The force, the change in the field that we are creating is monumentally different. So it's just silly to say you're bending the space as much as the Earth is bending the space. That's not true. Your contribution is infinitesimally tiny. The Earth's contribution is gigantic.
Just acting on opposite bodies.
So again, that diagram could be a way of defeating everything he's saying here. Is you could just do a dented space diagram and just show the gigantic difference in how the space has been bent by the two objects.
Pulling down on me, and I am pulling up on the Earth. But if I, get to a stepladder and jump off, I'm going to see myself move. I'm going to move so much faster. The Earth technically will be moving up to meet me, right? That's what I'm trying to say.
All right, so the Earth isn't technically doing any of that. It's not going to move at all. A few electrons are going to move. The Earth isn't going to move.
If the Earth is like right here, and I'm like, right, I'm about to fall down to the Earth, right? And I jump off a stepladder. Well, all we really see is myself falling down, but actually I fall down and the Earth comes up just a little bit. Why does the Earth only come a little bit? Because the acceleration of the Earth...
I mean, the little bit is so infinitesimal that you couldn't measure it. It's just nonsense.
It's so small you can't even measure it.
Right. So why bother talking about it?
And the acceleration of my body is so much bigger than that's all I ever see. But people think that the Earth isn't moving, but actually it does respond to gravitational influence, of course. But
so he says, of course it does. And I'm saying, no, of course it doesn't. The surface does. You can wave the surface of the Earth. You can create some vibrations on the surface, but you're not going to move the Earth.
The mass of the Earth is so big that this tiny amount of gravitational force isn't going to really move it at all. So we just treat it as stationary, is what I guess I'm trying to say.
Well, it is stationary because, yes, you just don't have enough energy to move all of the electrons and make them move to a new location. There's not enough energy to move the Earth. So all you can move is a few little pieces, and a few little pieces just go back to where they were.
So let me read my notes, make sure I got everything. Every object attracts every other object in the universe. If you have multiple forces acting on an object, multiple gravitational forces, then you add the resultant force up vectorially. In other words, Earth is acting on me, and they're producing these forces.
So you could just understand all the arrows as pointing, pushing arrows, and then you just do your vector math of adding the vectors. So blah, 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 blah. All right, probably as good a place as any.
Right here. If I draw the moon over here, right, then the moon is attracting me like this, and I'm attracting the moon, right? But also the Earth is attracting the moon, right, like this, and the moon is attracting the Earth like this. So you see there's all this interaction of forces going on. And if I want to figure out, like, what is the net force acting on me, then I have a vector here of a force and a vector here, which is another gravitational force, and I would have to add those vectors up mathematically to figure out how I'm going to move and what direction I'm going to move. And if you had many, many bodies, like in a solar system with many planets, then it's very difficult to calculate without a computer how something is going to move, because you can see the interactions are many-fold.
Well, it's obviously not that difficult because they did it to find a couple of planets. So anyway, we'll call that a video and such and so forth and whatnot. Yeah. So till the next time and such. And it's just sad that physics is so lost in these wrong axioms that they've accepted as notions of reality. And they never really thought about it, and the very idea that gravity is some mystical, magical, bent thingy and that we can't understand, when it's so obviously doing something real in this universe, which is it's giving objects momentum, and then it's heating the earth with that momentum. And you have to account for that. So you can kind of figure that whatever gravity is, it has to be part of some kind of thermodynamic heat cycle. So it's not a bent geodesic in any sense other than the sun's a bent geodesic in terms of how it creates photons. It doesn't really create photons, it just reflects energy, and by reflecting it at a higher frequency, it makes visible light. So infrared goes into the sun, visible light comes out of the sun. Okay. Anyway, so they got it all wrong. And I'm just sitting here as a poor slob who's got to live on a planet full of frankly obnoxious, arrogant dumbasses who belligerently will not listen to the truth. Sad, really.